Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. In this video we're going to look at Karnaugh maps some more, and we're going to look at don't care conditions. Don't care conditions arise when we do not care what the output is, or we do not care what that input sequence is. So it may be that we're not looking at that output at all, or it might be that we know for our system that input sequence will never come in, and so we don't care what the output is. A common example of this is when we're counting up to 9, from 0 to 9 for one digit in the decimal system. To go from 0 to 9, you need 10 rows of a truth table, which means you need to use a truth table that has more than 8. So you need 4 variables, you need 16 rows. And so you count those first 10, but then those last 6 you have no need of. And so those last 6 would be don't care conditions in your truth table, thus in your Karnaugh map, and then your expression will be simplified in that way. So we'll look at how to handle those don't care conditions and build ourselves a simplified boolean expression from that. All right, let's get started. All right, so we're looking at don't care conditions. And these will be marked with an X in our diagrams. All right, so let me build a truth table. We're going to go 1 0 0 0 1 0 0 0 X X 1 X and 1 0 1 0. Okay. So that means we don't care if the input sequence is 1 0 0 0. We don't care if the output is a 0 or a 1, because that doesn't matter to us. And the same thing for 1 0 1 1, and the same thing for 1 0 1 1. So we'll maintain an X as we transfer this over to our K map. So we have W X Y Z. Remember we're reading these in groups of 4, and we have to make sure that we skip our third column and our third row. And so I'm going to write this as 1 0 skip 0 0, and then the next group of 4 is going to be 1 0 skip 0 0, and then the next group of 4. Oops, I actually wrote this wrong. And here, I wanted to, I forgot about the skip myself. That's okay. And we'll just finish this up. I wanted this last 4 to be X, X, 1, X. Like that, and this to be 1 0 1 0. Okay, so skip here. And so this is 1 0 1 0. And then our last 4 is X, X, 1, X. So X, X, 1, X. Okay, that's the Karnaugh map that I wanted. All right, we got that. Perfect. Okay, so let's go ahead and then do our boxings on this Karnaugh map. And here's the rule. So we can box X's to make our boxes bigger. We don't need to box the X's. So essentially the X's can be 1s when we want them to be 1s, and we can box them to make our boxes bigger. And they can be 0s when we want them to be 0. So if I have no need of using the X, I can leave it outside of all boxes. Don't need to box it. So let's see what we have. So I can box this whole column, and inside my box there's only 1s and X's, so that is a valid boxing. I also see that I can box this complete row. Even though 3 of the 4 cells are X's, that is a valid boxing. And the last boxing is this 1 1 we need to get, right? This 1 in the corner. But we're trying to get the biggest box we can. I can see I can box these 2, but also I can wrap to box the 4. So we're going to box those 4, and that's our third boxing. And so we write our function now. I'm going to start at the top and just go down through each of them. And so this is the column 0 0 for YZ. So this is Y bar, Z bar. This is the column for at 1, 1 for Wx, so this is Wx. And then we have the two columns, 0, 0, and 1, 0. The thing that's the same there is z bar. And the two rows, 1, 1, and 1, 0. So the thing that's the same there is w. So we have w z bar. And there we have it. That's it. So we found our solution. Thanks for watching. As always, be sure you subscribe and like and leave comments if you have some. I'll respond to those. My name is Mike Stancic, and this is Digital Electronics Classroom. Have a great day.